Fly across almost any landscape in the country, and you're likely to see traces of diverse water systems that seem unconnected. Rivers and streams, lakes and ponds. But beyond what you can view is a far richer network of unseen water sources called aquifers that exist underground. Finding these sources is tricky, but here and there you see clues to water deposits that most of us depend upon for survival.
It's difficult to see an aquifer. Aquifers are saturated materials. We stand on top of the land surface, the aquifers are below us, so aquifers and groundwater become an act of faith. You have to believe that those materials below the land surface are in fact saturated, so we're looking at the character of the materials and the things that cause them to pack together with open spaces between the grains that will store and transmit water. Outcrops like this give us an idea of what the aquifers are like below the land surface. Oftentimes we wonder where the water is, and we can come to this point where you can go down and stand on that groundwater as it becomes surface water.
But elsewhere, the connection between surface and groundwater is far from clear. Beneath the Great Plains is one of the world's largest aquifers, stretching from the Dakotas to Texas. But other regions contain only a patchwork of aquifers, so locating them is no easy task. And as more states cope with ongoing drought, it's become critically important for leaders of natural resource districts to map and manage groundwater reserves.
This goes
Correct.
south, this goes north.
Yeah. Exactly.
Today, managers of the Lower Platte South River Basin are meeting geologists from Exploration Resources International to locate aquifers in their region.
So we connect the dots, we make a three-dimensional image, and we come up with a volume of the aquifer. This study will answer how large are the aquifers, how are they connected to rivers and streams and lakes, and how much water is in storage. That's the goals.
Traditionally, geologists have relied upon one costly and time-consuming method to find aquifers.
When we drill test holes, we're concerned about the character of the materials that store and transmit water. It's got sands and gravels and silts and clays. Depending on where you are, it can be just about anything.
And that's a challenge because test holes are usually drilled between great distances, every 3 to 6 miles. By analyzing samples layer by layer from each drill hole, geologists can map the water-bearing sands and gravels that form aquifers. But since the drill holes are so far apart, they can only estimate the shape of an aquifer between each site.
And then we would take a whole group of these drill holes and we would use our imagination and our training to fill in the dots.
Go on the next slide, you can...
For 150 years, geologists have been doing it with our imagination. Now we've got a new tool that helps fill in the blanks.
The new tool is called SkyTEM. SkyTEM is an airborne geographical survey system that maps aquifers electronically.
The structure looks rather fragile, but it's very robust. It is built out of almost non-metallic materials because the system that we use sees metal, so we want to minimize the metal that's in it. Attached to the platform on the front end of it is a magnetometer, and it measures the background of that particular site of what the Earth's magnetic field is doing. On the entire loop around the outside is a series of wound copper wires, and that's the transmitter. That's what sends the signal into the ground. All the helicopter is the vehicle that carries us. Everything is just quick clip to the bottom of the helicopter and off it goes. It flies at approximately 50 miles an hour, 100 feet off the ground. The helicopter will be 100 foot above that. What we would like to see is aquifer everywhere. We want water for everyone, every place. That's not the way it works. The aquifers are very limited in size and scope. Some of them can be many tens of miles long, and some of them are maybe a quarter of a mile around. It's hard to imagine how these aquifers interact They may be totally disconnected, or they may be very connected. We don't know that until we do this mapping.
As the rig flies back and forth along parallel lines, SkyTEM shoots rapid-fire radio waves into the ground every 9 feet to a depth of 900 feet, all the way to bedrock.
It basically sends a radio signal into the ground. The rocks feel that radio signal and then kind of get a little energy and send energy back out. It says, I'm a sandstone, or I'm a sand and gravel body, or I'm clay and silt. Well, that's what we're mapping. Is it electrically conductive, or is it electrically resistive? So the aquifer material is resistive. So that's what we want to see if you want to know where the aquifer is. If it's electrically conductive, that's the clays and silts. It's like what you would use with silly putty. Not much water gets through that. So that tells us where the aquifer isn't. Between those two, we map that difference and we make a map of where everything is.
Each SkyTEM signal acts as a virtual borehole that displays sediments in vivid colors. For geologists, blue and green mark water-resistant silts and clays, while yellow and red reveal the sands and gravels that make up aquifers.
When it's all done, you will look at a picture sideways through that map. You will be able to see what geologists always want to see. We want to know what's real. We want to know where our imagination is and where the reality is. The important part is when we're mapping, we know the difference between where we have aquifer material and where we don't.